we present HumanVDM, a novel single-view 3D human generation framework that leverages human video diffusion models and 3D Gaussian splatting to generate lifelike humans. 3D human generation aims to reconstruct 3D humans from a single-view RGB image without direct multi-view input. Generating 3D humans from a single-view image remains a challenging task since it requires modeling realistic appearance, accurate geometry, and plausible unseen parts that are not captured in the input image. Existing methods that apply multi-view diffusion models show progress but face inconsistent view issues, which hinders high-quality 3D human generation. To address this problem, we propose HumanVDM, a novel method for generating a 3D human from a single image, using video diffusion models. Extensive experiments and comparisons demonstrate that HumanVDM outperforms state-of-the-art methods in terms of generation quality and realism. HumanVDM has a very simple architecture that consists of 3 modules: a view-consistent human video diffusion module, a super-resolution and frame interpolation module, and a human Gaussian splatting module. First, a single human image is input into the human video diffusion module, which helps to generate a coherent human video. This video diffusion model is an SV3D model that is adapted for human video generation and is capable of producing consistent multi-view images. However, the video quality from SV3D for the human body is of low resolution and thus not satisfactory. To address this issue, we leverage CodeFormer and perform a 4x super resolution. Super resolution helps in improving the texture quality in the multi-view video. Since the generated views are not enough for appearance consistency, we perform perception-oriented video frame interpolation, also known as VFI. VFI helps to improve the geometric smoothness of the 3D human and the quality of the invisible areas. For it, the module inputs 2 referenced frame images and reconstructs an intermediate frame. First, it estimates bidirectional optical flows, using a motion estimator. Next, the motion estimator features are blended with multi-scale encoder features using asymmetric synergistic blending to obtain high-quality intermediate features. These features are finally decoded to obtain the intermediate frame using a conditional flow generator, which samples from a normal distribution. Next, the 3D human Gaussian splatting module is utilized to learn lifelike 3D humans under the guidance of high-resolution and view-consistent images. Gaussian splatting employs point-based representation, which facilitates high-quality rendering by modeling the human as a collection of parameterized Gaussians. Each Gaussian is characterized by a color, a 3D center position, opacity, a 3D scaling factor, and a 3D rotation. Here, we introduce an optimizable feature tensor, pixel-aligned with the pose feature, to capture the appearance of the reconstructed human. The parameters for each Gaussian are predicted by a Gaussian parameter decoder. These predictions form the 3D Gaussians in the canonical space. Using linear blend skinning, these canonical 3D Gaussians can be reposed into motion space for differential rendering. For formulating the loss function, we take the current frame image as the ground truth and calculate the loss with the rendered image. Here we present the visual results from HumanVDM on images with varying poses, genders, actions, diverse clothing, and different hairstyles. HumanVDM consistently achieves high photorealistic quality and precise geometric accuracy. Next, we compare HumanVDM to other SOTA models. Compared to HumanVDM, Pamir exhibits significant shortcomings in the geometry of the generated 3D human. For example, the body of the generated human is incomplete for the first image. On the other hand, PIFU, TEC, and SITH reconstruct remarkable geometries but contain apparent artifacts. Likewise, SIFU displays misalignment in character motion and suboptimal texture quality on the back of the generated human. Ultraman obtains good geometry but fails to predict the realistic appearance of unseen view. The results demonstrate that HumanVDM achieves superior generation quality. Here we present additional visual comparisons, along with another set of in-the-wild testing results and comparisons. In the quantitative evaluation of the T-human dataset, HumanVDM achieves the lowest LPIPs and the highest clip score, indicating that the rendered images produced by our method are highly consistent with the input images. Additionally, HumanVDM achieves the highest SSIM and PSNR scores, demonstrating that the rendered images of the generated 3D human are most closely aligned with the ground truth. In addition to quantitative comparison, following previous works, we present a user study to demonstrate the performance of HumanVDM. We conduct ablation studies to evaluate the proposed modules by excluding various components. Quantitative results demonstrate that our full model achieves superior clip similarity and SSIM across both all views and the front view. Visual results demonstrate that the 3D human generated by our full model exhibits more photorealistic textures and precise geometry. Although our full model shows a slight decrease in LPIPs and PSNR, the visual results indicate that the 3D human reconstructed by the full model is of higher quality. Overall, our full model achieves better performance while excluding the proposed components, which confirms the effectiveness of the proposed modules. Here we present the 3D spin videos to demonstrate the texture quality and appearance consistency of HumanVDM. Thanks for watching.